Hello, Mr. Colati here. Today we are going to continue our study of integrals or integral calculus by looking at boundary conditions. This is a short lesson, but we're going to zoom in on that plus c idea today. So remember, this expression is an integral. This means take the integral or take the antiderivative of 2x with respect to x. Hopefully you remember how to do this from yesterday. This is going to be x squared, and then we don't forget we have to write plus c. This entire thing is called the general solution. Now, think about this plus c. That's what we're looking at today. Well, technically this could be c equals 0. That would give me the curve x squared, which is just the mother parabola. Hopefully you draw it a little nicer than I do. Now, let's take another value. For example, c could be 2, which would be a vertical translation up by 2. So it would be the mother parabola moved up. So it could be like this. So that would be y equals x squared plus 2. What's another example? Say c could be minus 2. So then it would be the mother parabola but moved down. So that would be y is equal to x squared minus 2. And you can you can imagine that there are any different number of combinations of this, right? There's so many different possibilities for c. So the question is, which curve is correct? Which curve is correct? And we'll find today that we can find out by using any boundary conditions that are given to us. Now, watch. We're going to do some questions today where we are given some boundary conditions. So, for example, here's a function, or find the function if the derivative is 2x and the curve passes through this point. This here is a boundary condition. So, if the derivative is 2x, the function itself is the integral of that, which is x squared plus c, as we just saw. Now, every year I give a question like this on I forget if it's a quiz or a test, and students just give me that answer. Well, that's part of the answer. That's a few marks. But I also need to, and that would be correct if I wasn't given this extra information. But this extra information means I know I can figure out which curve it is. I mean, think about it. If you know this x squared plus c has to pass through this point, you should be able to figure out which quadratic it is. How do you do that? Well, you sub in that boundary condition into my equation. So I get 9 is equal to 2 squared plus c. 9 is equal to 4 plus c, so c is equal to 5. Therefore, my function is x squared plus 5. I know which one of these quadratics it has to, one of these parabolas it has to be, because I know that boundary condition. Neat. So it's not too bad. This is just an extension of our lesson from yesterday. Let's try the second example. Given that the function f of x, given that the derivative, oh my god, the second derivative. Oh, we didn't really do this yet. I skipped that lesson because it's not really in anymore. Oh, whatever, too bad. So you can imagine that the second f prime prime double prime, this is the derivative of the derivative. And so we have some more information. The gradient at point 1 comma 5 is 2. Remember, the gradient is the slope or the derivative. Okay, I know you don't like this double prime. I had to pull out that lesson because it's not formally in anymore and we didn't have time. But I mean, this isn't the hardest thing in the world, right? If I have f of x is equal to x to the power 5, The derivative of that is 5x to the 4. The second derivative is the derivative of the derivative. It's not too crazy. You can keep going, actually. You can do the fourth derivative, fifth, sixth, etc. We really only use the top three. Okay, so if I know, so first of all, if I take my double derivative, I can go back to the derivative by finding the integral of it. And this is going to be, okay, x squared, and this would have to be a 3, so 2 times 3 gives me 6, minus 2x plus c. I'm going to call this one c1. Now the problem is I have this unknown constant. Can I use any of the information to help figure it out? Well, I know that the gradient, aka the slope, aka the derivative, so this value, at this point is 2. So I know, therefore, we know the slope at x equals 1 is 2. Therefore, the derivative at 1 is equal to 2. Because I've been given the derivative at this point, x equals 1 is 2. The gradient is 2. So then that means I can sub 1 comma 2 into this expression I just found for the first derivative. So that's 2 is equal to 3 times 1 squared minus 2 times 1 plus c1. 2 is equal to 3 minus 2 plus c1. So 2 is equal to 1 plus c1, so c1 is equal to 1. Therefore, the derivative, the first derivative, is equal to 3x squared minus 2x plus 1. Okay, now this isn't enough though, because I need to find the original function. So I need to now take the integral of this, the integral of the integral. The enemy of my enemy. So I'm going to take the integral of that with respect to x. Let's do it. So this is going to be x to the power of 3. That's okay. Minus x squared plus x. And I'm going to find another constant. This is going to be c2. Now, do we have any boundary conditions for this? Well, yes. We know that there's a point on the graph, 1 comma 5. So I'm going to sub 1 comma 5 into f at x. So I have 5 is equal to 1 cubed minus 1 squared plus 1 plus c2. That gives me 5 equals 1 minus 1 plus 1 plus c2. So I get 5 equals 1 plus c2. Therefore c2 is equal to 4. Therefore I get my final answer. F at x is equal to x cubed minus x squared plus x plus 4. There's my final answer. So we had to do the process twice, but we basically use the information given in the question. Sorry about this higher order derivatives. That little thing that we didn't really see before. Okay, let's turn la page. And we'll do one more example. This is a real world question. A classic IB question too. They like to do these sometimes. The growth rate of a city's population is this derivative. Now, does this make sense? All right, it's the growth rate. So the change in n over the change in t. Remember, we kind of can think of this as a slope formula. So change in n over change in t, where t is the years after 1995 and n is the population. So the change in, right? So this is a change in, it's a rate, but we want to find the actual function n. So that means I need to find the integral of this expression. And all of this is a boundary condition. Right? In 2000, the population was 3,200. That means that n at 5, because it's 2000 is 5 years after 1995, is 32,000. And then we want to find out the population, the n value, when t is equal to 15. So that's what the question's asking. What is n when the t is equal to 15? Well, first I need to figure out what n is. So let's start with dn dt is equal to 400 t to the 1.05. Now, to find n, to undo the derivative, I have to take the integral of this expression. This is confusing. Let me take the constant out. That makes my question a little bit easier. And now let me be really careful. I apply I go backwards to find the integral correctly. So the t, I'm going to add 1 to, so I get 2.05. Now, if I took the derivative of this, there would be that constant. So I actually need to divide by 2.05. And then be careful, don't forget plus c, or you're going to forget to do half of this question. If you check my answer, the 2.05 comes down, and this would cancel out, and then it would subtract 1, so it does go back. Let's do all my subs. We could simplify, but let's do the next step, which is sub in my boundary condition, which is here. So we know n equals 32,000 when t equals 5. Therefore, we sub in 5, 32,000. So here we go. 32,000 is equal to 400 1 over 2.05. T in this case is 5 to the 2.05 plus c. Now we just have a whole bunch of math to figure out. Well, this is actually just all a number. So let me say c is equal to 32,000 minus 400 over 2.05, 5 to the 2.05. And now let me just very carefully type this into my calculator. I'm going to do it backwards, kind of. 5 to the 2.05 times 400 divided by 2.05. So now it's 32,000 minus that answer. So let's try that again. 5 to the power of 2.05, okay, times 400 minus, or divided by 2.05. And now it's 32, 1, 2, 3, minus that answer gives me 26. That seems to make more sense. So then I get 26,713.17 9. Okay, therefore I now have an expression for n, which is 400 over 2.05 t to the 2.05 plus 26,713.179. Now you might be thinking, Mr. Colley, why didn't you just simplify this? You could have simplified this into a number. You're right, but what's the question asking for? The population, what will it be in 2010? Like, they don't care about, I mean, they want to see that I've done this process, but they don't care if it looks beautiful, right? I need to do what I need to do in order to get to this final answer. So I'm just going to keep pressing along. I can even put a little box around it. I mean, what's neat is I use my boundary condition to find an answer. So now I'm going to sub in t equals 15 because I want to find the population, n, when t is equal to 15. So now n at 15, well, this is the easy part. I just sub it into my formula I just made. Okay, and what's neat is that you can just use your calculator. So watch this trick. Hopefully you guys know this trick. I'm just going to leave this in my memory so I have all the extra digits, and now I'm going to add it to this other expression. So plus 400 divided by 2.05 times 15 to the power of 2.05. My calculator can do order of operations properly. Yours might not be able to. And it does all that, and it gets my final answer, which is 76,981.364. So I'm going to finalize my answer. Therefore, the population will be 76,981. Oh, sorry, and there it is. So that was a real life question where we had to use boundary conditions. This is a pretty easy, straightforward lesson, but I'm telling you, every year we get a question like this, and a lot of students only answer up to here. Then they forget the plus C, and they think they're done, and they got 2 marks on an 8-mark question. Make sure that if you're given boundary conditions, you're given extra information, you need to use it in the question. The answer to this question should be a population in the year 2010. Don't forget boundary condition, and be careful with this, right? If you're given a rate, to go backwards, you have to find the integral. Okay, so our homework for tonight is page 296, number 1 to 5. I'm just going to make a quick note here, because we didn't really touch motion, and we're not going to until grade 10. But you'll need to know this for your the section you're going to work on. The derivative of a distance time graph is velocity. The derivative of the velocity time graph is acceleration. So that's something you might need to know for the word problem. And that's going to come up. This is something we're going to spend a lot of time on in grade 12. Okay, good luck with that, and we'll see you next time.